All right, hello everyone. Welcome to the stream. Welcome to the live stream. Unfortunately, I couldn't make the live stream work, so this will be a presentation that I'm recording from home. But rest assured, all the other live streams should go ahead just as normal. For our first topic, let's dive into something complicated. For the Year 13 students will benefit mostly from the complex number revision. So let's have a look what is on our agenda for today. We're going to go through three topics. We're going to talk about surds, solving equations, and eventually all the information that you need for your complex numbers. Before we, however, start, I would like to talk a little bit about effective learning strategies. I want you to make the most out of your notes, your revision time that you have. And remember that these learning strategies can also be used for other subjects, not just for mathematics and statistics specifically. Make sure you stick around because right at the end of the presentation, I have a surprise for you. And if you follow through the whole presentation, you will mainly benefit from that one at the end. You'll be able to see what we see right at the end. I would like to just mention that majority of these concepts that we talk about today are the fundamental topics of the calculus, of the complex number part. Here it is important to remember that you might remember some of these contexts, some of this you might have to remember, but all of these concepts are going to appear somewhere in your exams. There might be a question that is testing you on multiple of these concepts in one go. There might only be a question that asks you for one of these concepts. So make sure that you are aware of all the concepts that we talk about today. Make sure that you go through, take notes. If there's something that you're not sure about, a topic that you have forgotten perhaps, or you didn't realize you need for the exams, make sure you pause the video, take your time, write down some notes. All right, get ready. Have a pen, a paper, and your scientific or graphics calculator ready, because if we need them, we might be able to get you to go along, do the same as what we're doing in our lessons so you know which buttons to press. Now for today's goal, today we will be reviewing all the fundamental knowledge that you need to know to pass and do well in the complex number examination. Our goal today is not to go through past papers or to look through example questions. We will do that in our future streams. Today, we're mainly going to make sure that every part of the knowledge that you're required for the exam is ready for you. Just a quick introduction. My name is Marcel. I have been a mathematics and statistics tutor for the last 10-12 years. And I've actually built my own tutoring company to help more people learn. And now it's time to be able to give all my experience and all my knowledge to you via free lessons online. This is the idea of my channel. There will be more videos, especially next year when the new the school year starts. There will be tutorials, there will be courses, structured ways for all the content that you need to know for mathematics, especially year 11 to 13. For our pre-topic, let's talk about the learning strategies. The first part that I want to talk about is active recall. This comes from the research over and over and is one of the most efficient ways to learn. And when I talk about active recall, it can be really easily achieved. You're probably already looking through your notes. Now, all you need to do is flip your page, turn it upside down so you see nothing, wait a few seconds, and then try and remember all the information on the sheet. Can you explain the information that was on your notes? This will be difficult in the beginning, and you're allowed to go back and check your notes, but then flip it again and try again. This active recall part will help you learn for long term. If you want to use cue cards, that's basically the same idea, but it might be a little bit too close to the exam. But if you're watching this in a future time and you have much more time to prepare for this exam, then cue cards are a fantastic way. Repetition is key. So what I mean with this is not to do the same notes over and over. I'm talking about spaced repetition. So on Monday, on Tuesday, on Wednesday, every single day of the week, you should be looking at your notes. Not an hour, not 2 hours long. Just take a few minutes, read it, try and active recall once or twice and leave it. Perhaps you want to just do that one more time before you go to bed. Read your notes for 5 minutes, put them aside, and try again in the morning. You will learn much, much more efficiently than if you have a 4 or 5 hour study period on a Friday to try and cram everything in. Self-talk is a very common strategy that we use even in problem solving or when we encourage students to think of how they're going to do their exam questions. Create a little conversation in your head. Create the situation where you're talking to yourself mentally. You would like to ask yourself questions. What was this again? How does this work? How does this link together? Because that will help you in the long run to be able to memorize more. Okay, so let's have a look at our first question. We're talking about surds. So what are surds? Surds are all sorts of roots. Nth root, the square root, cube root, and so on. So let's have a look. First, we need to talk about exponents, powers of numbers. So here's some examples. We've got our x squared, 2 to the 4, and here we can see all of them have some kind of power. We need to know one of the more important rules, that x to the power of n over m, a fractional power, means the mth root of x to the n. I usually just tell my students, if you just remember this one rule, you can get to that formula yourself if you don't have it in a formula sheet. If you just remember that x to the power of half is the square root of x, then you can get to the rule yourself by checking where's the 2. The 2 is in the denominator, and that's a square root, so that means whatever is in the denominator is the mth root. The number in the top, in the numerator, is then the power of whatever we have inside the radical. Let's look about adding and subtracting these powers or these exponents. Now, when we have terms, we can only add and subtract terms with the same base. So we cannot do anything in terms of, for example, x to the power of 3 and x to the power of 2. They're different terms. So we can treat these surds like variables when it comes to the algebra. So let's have a look at an example. The square root of 2 plus the square root of 3, they cannot be combined. They have a different base. One has 2, the other one has 3. Even though the power is the same, the power to 1/2, they cannot be simplified in any way. So let's have a look at the next question. We have square root 2 plus 2 times the square root of 2. Now here we have the same base. We have the same base 2. So we can combine all of these terms together. In this case, we have 1 times the square root of 2 and 2 times. So we treat it like a variable, which is 3 root 2. What about multiplying and dividing these terms? So you should use fractional powers when dealing with difficult exponents. What that means is you should write the x to the 1/2 instead of the square root x to make sure that you have numbers to deal with, not just the radical, the square root sign. So what's the rule for multiplying? As long as the base is the same, x to the power of a multiplied by x to the power of b is x to the power of a plus b. If we're multiplying terms, we're adding the powers. Well, for division, this follows. It's very similar. If we're dividing terms that have the same base but different powers, then we subtract these. Just a note, the base must be the same. Now, when we talk about multiplying and simplifying surds, we kind of have the same rule, but what we can do for the radicals, we can split them apart only if there's multiplication. So the square root of x times the square root of y becomes the square root of all x times y. This is the way of simplifying these kind of surds, and is similar to kind of like the simplifying of fractions. Our goal here is to have a perfect square in front of the radical. We want to take anything out that we can. So let's have a look at this example. We have the square root of 24k. First, we can write 24 as a product of prime numbers, 2 times 2 times 2 times 3 times k. And we recognize that there is a way of writing a perfect square. 2 times 2, that would be 4. So every time when we have a perfect square, we can take this outside the square root. The square root of 2 times 2 is 2 itself. So we move that out and we're left with everything else. Now 6 is not a perfect square, so we leave it in the radical, and the same with our number k. Rationalizing the denominator is a term that we use for simplifying irrational numbers. Irrational numbers are the numbers with the surds, powers. Here, this is kind of like simplifying fractions. We don't want any surds in the denominator. Yeah, so what does that mean? Let's have a look. We want the square root of 2 divided by 2. We're happy with this fraction, but we're not very happy with the fraction 1 over the square root of 2. Now, when you're doing calculations, it doesn't matter what form you have. Finish the whole question, but at the end, when you have your final answer, you want to present this in this form where the surds are in the numerator only. So let's have a look. What do we actually need to know? In order to change this, we need to multiply by a fancy 1. Now, when we multiply by 1, it doesn't change anything. 3 times 1, 4 times 1, it remains the same number. Now, we can write 1 as a very complicated term. So in this case, square root 2 over square root of 2. We're still multiplying by 1, so we're not changing the value of this term, but we are changing the look. So let's have a look here. We are now taking our 1 over square root of 2 and we're multiplying by square root 2 over square root 2. Top times top gives us square root 2 in the numerator, and the bottom times the bottom gives us the root 2 times root 2. And since the square root are opposites to squaring, this will just be 2. And we get the answer as above. So square root 2 over 2 is actually the same value as 1 over square root of 2. Now, when we talk about this, sometimes there's a more complicated question where we could have addition and subtraction in the denominator to make it more complicated. So here we're going to be using the conjugate. Now, we create the conjugate by simply changing the sign. So let's have a look what we mean. So the square root of 2 plus 1 has two conjugates, square root of 2 plus 1 or negative square root of 2 plus 1, because we can kind of switch plus and minus around. So either one of those will work in your calculations. So for combinations of rational and irrational numbers in the denominator, let's have a look what we need to do. We actually want to multiply by the conjugate divided by the conjugate. This is now our fancy 1. So here we can see 1 over the square root of 2 plus 1. We want to get the square roots out of the denominator, so we multiply by square root 2 minus 1, both in the top and the bottom of the fraction. Here's an example. It was taking a little bit long to put all the to put everything in nicely for the slides. So let's have a look at this example. We have 1 over the square root of 3 plus 1 over the square 1 over the square root of 3 plus square root of 2. And here we need to multiply by the conjugate. So we just flip the sign in the bottom to make it a minus. Now we can see top times top gives us the square root of 3 minus the square root of 2. Again, they're different bases. We can't simplify those. But in the bottom, we get the square root of 3 plus the square root of 2 multiplied by the same expression with a minus. Now, you can do the expanding separately and figure out what happens, or you can use the formula a plus b times a minus b to figure out what this is in one step. Yeah, basically we can see that the middle term always falls out, and it's just the end terms that stay squared. So we're going to end up root 3 squared, root 2 squared, and in the formula, it's always going to be a minus. Now, square roots and squared, that's very nice. We can get rid of those in our next step. So here we can now see that we only have a 3 minus 2 in the bottom, which is easy, which is 1. The top, again, we can't simplify, but dividing by 1, we don't need to write a fraction anymore. So we have our final answer. Okay, now let's talk about a little bit about solving these equations. Let's have a look at some quadratic equations. By now you should know the formula of a quadratic in the standard form, which you can see here, a squared plus ax squared, plus bx plus c. Now, if we want to solve for roots, what does that mean? Basically, in the real case, we're looking for points where it crosses the x-axis. Yeah. With other words, we want to set y equal to 0 and solve for x. So here we have this the same equation, substituted 0 in for y. Now, the standard way that we would now do, that you've probably learned last year, is to factorize, solve each for 0, and that all works fine. But in this exam, you can simply use other ways to do this faster for the exam. One way is to use the quadratic formula, which we have here in the top. We will come back to that in a second. And also you can complete the square if you're very good at this method, but again, it takes time. Or you can simply use your calculator, which is the method that we're most likely going to be using. So let's start with our second topic, which is everything on how to do the solving of these equations. Now, when we're solving equations, we're mainly looking at quadratic equations, some cubic equations in this topic. So you will have a formula sheet where you get the quadratic formula. So you can see on the screen, we have minus b plus minus the square root of b squared minus 4ac, all divided by 2a. And you recognize that the values a, b, and c come from the standard form that we've just discussed for the quadratic equations. So this is simply simple because you can just find the coefficients, the numbers a, b, and c, and substitute them into the formula. But what does this formula actually find? So if we substitute in a, b, and c, we need to calculate this twice because we have plus and minus the square root. Most calculators don't have a button for plus and minus, so we have to put this whole equation in the calculator with a plus and then again with a minus and write down both of the answers. Now, for this question, it is very important to understand that solving for these roots means we're looking for these x-intercepts in the real case. So, in complex numbers, and we'll see that a little bit later on, a quadratic will always have two roots, no matter what. This is not always the case in the real numbers. Yeah, in the real numbers, we have a problem here. We have a square root, and a square root is dangerous when we only have real numbers. Let's have a look at this quadratic here. It's a very simple quadratic. We just have x squared minus 1. We just moved the normal parabola one step down. And here we can see the roots that we want are at minus 1, 0 and 1, 0. Here, these are the x-intercepts that we're looking for. So remember, when you're actually writing down what the x values here are, remember for each of these to switch the sign. In this case, it wouldn't matter because they're both 1 and minus 1. What about this one? How many roots does this one have? We have one exact intercept with the x-axis, and that's exactly at the point where we have the vertex. What else can happen? Well, we could also move our graph up another unit. Then we get a parabola where the difference between the x-axis is always positive. We always have a function that is above 0, a function value above 0. Here we have no intercept with the x-axis. So where does this come from? How do we know which one of those situations we're in? And it's important that you remember that the discriminant tells us what situation we have for the roots. What is the nature of the roots? Remember, in the real case, we can have 3 examples. We can have 1, no real roots, exactly one root or two different roots. So the same here. So the important part is the discriminant can only be positive. So in real numbers, square roots are only defined for non-negative numbers. X has to be greater or equal to 0. We cannot take a square root of a negative number. The discriminant comes from the part where the square root part is in the quadratic formula. But be careful, the discriminant is not the square root included, it's just the part inside the square root, b squared minus 4ac. This value is, if you calculate this value, it is the number underneath the square root. So whatever that value is, that will tell us if the square root is well defined or if it's not defined. We need that number, the discriminant, to be positive for us to have two solutions. Why does it have to be positive? Well, because we can think of the quadratic formula having a plus and a minus in front of the square root, which will give us two different numbers, a positive and the negative respective number. If we have a negative number for the discriminant, then that whole square root cannot be calculated. And your calculator, if it's not in complex mode, it might tell you a math error or an unknown error or something else depending on your calculator. So that will tell us there's no real roots. We don't have any x-intercepts in the real numbers. There's one more case, and that is if the discriminant b squared minus 4ac is equal to 0. Now, why does this give us exactly one solution? Well, we're going to have the square root of 0, which is 0. And then in the formula, we have a plus and a minus. Positive 0, negative 0, all the same. So we end up with just one number. Now, in the complex numbers, we can actually solve the square root of x where x is 0. We can take square root of negative numbers, and we will be doing that a lot. This is the reason why we always have two solutions, because we will find a way on how to solve for those two parts where we have a negative and a positive of a square root, where the number underneath the radical is negative. Now, more again later. Remember, we're doing all the complex part at the end. We first are going to do all the fundamental knowledge that we need to answer questions that might not have complex numbers in them at the end. So, if we wanted to find the actual roots, we can use the quadratic formula for complex numbers as well. Both work whichever one you're in. So let's have a quick calculator tutorial just to have a look how we're going to use our calculator, and let's have a quick look. So I've got my calculator here, and you can follow. If you're going to be using this to solve when your calculator, you need to go into menu, and we're going to go into equation, and we can just go and scroll down. I'll have to use my mouse and my keyboard. There we go. And now it gives us three options. Simultaneous equation means you're solving multiple equations at the same time, which is not what we're doing here. We have polynomials. Of course, a quadratic is a polynomial, and I would highly recommend to stay away from the solver altogether. So now it's asking us for the degree. Here we have to press F1, which is 2. The degree is the highest power of the polynomial. In our case, it's the squared. And we can see at the top, it will give us the equation that we're looking at. It is important that you put your equation in this form, and it has to have an equal 0 when you want to put this in. So let's just put in some numbers. Here, for example, we can put in maybe 2 for 2x squared minus 1 and 0. This would be 2x squared minus x plus 0 is equal to 0. Whatever coefficients you have, put them in, and we press solve. And now we can see there's two roots. One at x is a half, and one is at x is 0. Knowing this, I assume you all know how to do this, but just to make sure, this will be a great time saver in the exam. Now let's have a look what happens if we go to equation and we put in one of the equations that has no real solutions. So let's go back to the solver, polynomial, degree 2, and let's put in the x squared, so 1, plus 0x plus 1. That was the example where we moved the x squared parabola up so it didn't hit the x-axis. And now you can see my calculator actually gave me an answer. It gave me I and negative I as the roots. Now your calculator will probably tell you that there is an error, and in order to be able to show complex roots, which you will find much easier to have this equipped, is you need to go to the normal page on the calculator and press Shift menu for setup. And if you now scroll down, make sure the mode is in complex mode. And what you want to scroll down to complex mode. And here you usually have real. If you reset your calculator, this will be on real. You want A plus BI in order to give you the answers. This will then display these complex solutions. Okay, let's continue. So one of the big theorems that we have here, now a theorem in mathematics is like a rule. It's something that someone has proved and it's very useful for us, a useful rule. So it's called the factor theorem. So when do we actually want to use this factor theorem? And this is when you want to find a factor of a polynomial. Now remember, a factor is part of the multiplication question. So factor 1 times factor 2 is the product. So with other words, we want to find something that divides the polynomial. If we have a polynomial, we have an equation. So it could be only another equation that is a factor to this. Now, that all sounds very complicated. It is actually very easy to apply this theorem. And if we want to know that x minus a is a factor, so remember, if you write your quadratic at x minus something and x plus something in the factored form or the root form, these are the factors for the polynomials. So here, if we want this to be a factor, all we need to do is substitute that number a into our original equation, and if it's 0, we have a factor. Why does that make sense? Well, remember, a factor means x-intercept. So if we have an x-intercept, y is 0. So we will expect to have 0. Let's have a quick example. Find the factors of x cubed minus 2 x squared plus x minus 2 is 0. Now, in order to find the factors, what you really want to do is you want to try some numbers out. Now, it's going to look like magic because I'm going to give you those numbers, but I can tell you, I tried 4, I can try 5, I can try 6. If it all doesn't seem to be working, I'm hoping that I have some luck with some of those special numbers like 0, -1, and 1. These are the 3 that you should always try, and in an exam condition, these are usually the ones that work. Let's have a look here. I substituted in 2. I mean, I did the question first, checked it, and then I gave you the answer. You could have tried 1, and we'll have a look what happens then. Here we have p of 2, so we think 2 is a root, so x minus 2 is a factor. And if we substitute this in, we get 0. And then the factor theorem tells us if you substitute in 2, then x minus 2 is a factor. So x minus 2 is a factor. This is all you need to know. Now, what we can do is we can rewrite this equation as x minus 2 times x minus something times x minus something else. Now, you probably wouldn't have thought of this, but 0, 1, -1, if you're doing complex numbers, I and negative I are also good numbers to put these in. So if we substitute in p of I, so we're going to substitute in I for x, and we simplify, we also get 0. So x minus I is a factor. Now, we will figure out later, or you might already know, but if I is a factor, then so is the conjugate of I, which is minus I. So, a possible exam question that you might get is very similar to this. It's going to give you a function p of x squared plus 3kx minus 5 is divided by x minus 1, and the remainder is 1. Find the value of k. So what we did before is we checked if x minus 2 was a factor. And if that's the case, then if you substitute it in, then you get 0. Now here, remember this is in the form x minus a. So here the number that we need to substitute in is 1. But we already know that x minus n is not a factor. So why are we using the factor theorem? Well, the opposite of being a factor, right, is that we can divide it by that, but then we have a remainder. So there's only those two situations. It's either we have a factor or we have something with a remainder. Here in the question, they're going to tell us what the remainder is, and all we need to do is substitute in that number, x minus a, so in this case 1, and it will tell us the remainder. So it will be equal to 1 instead of equal to 0. So we're going to substitute in p of 1, which will simplify to 3k minus 4. I assume at this point all the simple algebra you're happy to do yourself. If you're not sure, pause the video, go through the questions and calculate them yourself. Okay, now we know that the remainder is 1, so we can set p of 1 equals to 1. So what we're going to get is that 3k minus 4 has to be equal to 1. And this is a simple equation that I assume you can solve for k is equal to 4 over 3. Now the remainder theorem, we've just kind of talked about this. We use this to find the remainder when dividing polynomials. The rule is basically the same. So if you're dividing a polynomial by x minus a, then you can substitute a to find what the remainder is. Just like we did before, p of 1 was equal to 1, the remainder. So, and again, what does it mean to have a remainder 0? What does that mean? Well, if we have a remainder 0, then we could divide it perfectly, which means x minus a is a factor. Another example real quick. So find the remainder of p of x is x squared minus 4x plus 5 when it's divided by x minus 1. Well, the remainder theorem is just telling us all we need to do is substitute in, and that's it. Now it says x minus 1, so we substitute in positive 1. P of 1, and we get 2. So we have the remainder is 2. So what does it actually mean? Well, that means that when we divide the polynomial x squared minus 4x plus 5 by x minus 1, which is our first term here, then what we get is we get something that divides it perfectly. We no longer have a fraction, plus we're going to have a 2 remaining because we still have 2 that needs to be divided by the denominator, similar to long division when you have your remainder. Now, the remainder theorem does not tell us what this number is. X minus 3, I had to calculate that myself doing long division for polynomials. Now, most of the time, we don't actually care what we actually get for this full expression, so we only care about the remainder, which is why this theorem is so easy. We don't have to go through the steps and do long division with polynomial equations. Awesome. Now we get to topic 3. Complex numbers. There's going to be quite a bit. Make sure that all the concepts in this are understood, that you remember them, and you've got them ready when we tackle all of those past paper questions, when we tackle all of those examples that we are going to do next in our next lesson. So first of all, for the fundamentals, I, the imaginary number, you should know this by now. I expect that you know this. Yeah. We define that number I to be I squared is equal to -1, or if you like it more, you can have I is equal to the square root of -1. Both of those definitions are equivalent. Now, using I, we now can take surds or square roots or any of our surds of negative values. So how do we do that? The square root of -5 is equal to the square root of 5 times -1. And remember previously, we could separate those surds by just splitting them up term by term. So here we get the square root of 5 multiplied by the square root of -1. And by definition, the square root of -1 is I. Now, you've seen this probably once or twice, and now you don't do it anymore. All you need to remember is if you've got the square root of -5, just write the square root of 5, take the negative, leave it out, we don't need it anymore, but remember to put the I at the end. Now, for the rule, simply make the number positive under the square root and multiply by I, just like I've just told you. You should have heard and be somewhat familiar with rectangular form for complex numbers. Now, a complex number always consists of two parts, the real part and the imaginary part. Here we have z, a complex number, is a plus bi, where a and b are real numbers. And it's important to remember that both parts, a and b, are real numbers. The only thing that makes this a complex number is the fact that we have bi, a real number, multiplied by I. Let's have a look at a quick trick. Like often in exam questions, they use z to represent a complex number. You see this all the time, z or w or v. These are very common letters or variables that are used to show it's a complex number. X, however, and y are often used for real values, real variables. Now, when you see these, it is going to be very difficult for you to answer questions unless you start with the most important part. Let z equal to a plus bi. Even if the question doesn't need it, I recommend that you write this in every single one of your questions if they haven't already given it to you. The reason is because most of the algebra, most of the concepts that we do requires us to know A and B, the real and the imaginary parts to this complex number. So, just like we said, it has two parts. So we have a real part, and make sure you recognize how we note down the real part. It's RE of the complex number. And in our form, a plus bi, a is the real part. The imaginary part, and this is what students always get wrong, it is the part that has the I in it, yes, but it does not include the I. It is b in our situation, a plus bi. So if you want to find the imaginary part of any complex number in rectangular form, make sure that you do not include the I when you want to calculate something or talk about the imaginary part. This is where majority of students get it wrong. Also remember, Im of z is the imaginary part of the complex number z, which we represent as b. Yeah? Do not include the I in the imaginary part. So let's identify the real part and the imaginary part of the following. Very easy, you should know this. Yeah? So z is 5 plus 2i. 5 doesn't have an I, so that's your real part. 2i is your complex part, so we have 2 as the real part in front of the I. So our real part is 5, our imaginary part is 2. Z is minus 1 plus 1, have a think. Minus 1 is the real part, and what is the imaginary part? The number in front of the I, which is 1. What about z is 2? Well, complex numbers need to have a real and an imaginary part. Here we don't have an I, so we just have 2. That's our real part. We still need a plus bi. But in order to get rid of the I, b needs to be 0. So our real part here is 2, and our imaginary part, on the other hand, is 0. Complex numbers are bigger than the real numbers. So we have all of the real numbers included, and then we put the extra numbers that are combinations of real and imaginary. We put them all together. So a real number itself, like 2, is still by definition a complex number. We just have b, the complex part, the imaginary part, I should say, equal to 0. What about z is minus 1? What I've just explained should help you here. Remember, here we have -1 in front of the I, so that's our imaginary part, but our real part is 0. Well, and it doesn't matter what the number is, it all goes the same way. Just be careful. In this situation, I put the I first, square root 2i, because we can flip addition and subtraction. So the real part here is square root 5, and the imaginary part is the square root of 2. Now, you should know that in rectangular form, we want to present a way that we can visualize our complex numbers. We want to be able to see what we're looking at. We're a very visual species. So let's have a look. The Argand diagram is kind of like a coordinate system, but we use a complex plane. So that means for the x-axis, we have all the real numbers. That's the real part that we put in. But for the y-axis, we actually put the imaginary part. So here we actually see our complex number as x plus iy. Some people use a plus bi, some people use x plus yi. It's the same concept. Also, if you have the I in front of the Y, like in over here, that is not an issue at all. Because remember, it's multiplication. IY is the same as YI, same way. So how does this diagram work? We need to know the real part and the imaginary part, and the real part is on our x-axis, while the imaginary part is put on our y-axis. Just like you know from coordinate system, for any other functions that you've done before, we can plot these in the diagram. Often we use an arrow from the origin 0, 0 to that coordinate to represent that complex number. Now we'll come back to the r and the theta. You probably know what it is, but let's leave that for a little bit later. Oh, never mind. Let's talk about it right now. We've just talked about the rectangular form. We have a second form that we want to use for our coordinates. We could have actually learned this much earlier and used it as an alternative for our xy coordinate system. It works for real numbers or other functions in different coordinate systems as well. So let's have a look first of what we do before we discuss on why this is so good. Instead of giving our points in x and y coordinates, we use polar coordinates. The same way, open bracket r, comma, theta. Theta, you should have heard theta by now. This is the angle. Yeah, this is a Greek letter in the Greek alphabet, always used to represent angles. So, going left and right, up and down, that is going to be replaced. Yeah, if we want to show you where we are on the coordinate system, we will no longer tell you, go 3 steps to the right, turn around, go 5 steps up. That's where our coordinate is. That's what the coordinate system did before. Instead, we need a different way of showing someone where to go. And if you think about it, if you tell someone where to start, you can tell them the end point by showing them how far do you have to go and which direction do you need to go. Well, if I'm telling you to go this way and you need to go 20 meters, I have an exact point of where I know you're going to be at the end. I could represent that by telling you go this many steps right and then this many steps up. It will be exactly the same number. So these two forms show us the same complex number, just in different forms, in different ways. So now we're going to start at the origin when we use polar form. At 0, 0, we're always going to be there. And we're going to be moving from there in any direction. So now we need to know where we're going. So we need a direction, which is the angle. And the angle that we measure is always going to be from the positive x-axis. So if we have the positive x-axis, we start here and we move our angles all the way around to see where we get to. Our angles in this case are measured in radians. So make sure when you're using the calculator, make sure to put it in radians, not degrees. Now, if I'm telling you the direction, go this way, I also need to tell you how far to go to tell you exactly where the point is that I want you to be at. So the distance they travel is here given by r, and you can think of r as the radius. It will tell us how far away our complex number is from the starting point, which again is the origin. Now, you have used this notation before, CIS. Well, let's have a look. What is that? For CIS pi, or for cis pi, is exactly this polar form. It tells us how far to go, 4 units, and it tells us the angle, pi. Now let's go back to our diagram that we've just had, and we can see that the same complex number, x plus yi, where we went x steps to the right and y steps up, can be represented by showing us the angle theta, where to go, and r, how far to go. Why do we use cis, and what is the meaning of it? So cis is a combination of c stands for cosine, I is the imaginary number, and s stands for the sine. So if we combine them, it's the cosine of something plus I multiplied by sine. 5 cis pi over 2, however, now means the following. So we're going to have 5 times cosine of the angle, 5 cosine pi over 2, plus I, 5 sine pi over 2. So if we wanted to look at this and expand this, what it actually means, what the abbreviation CIS means, we need to write it as a function of cosine something, sine something, and here we can see the I is always linked to sine. Whatever you use for the angle, the sine of the angle is going to give you the imaginary part. That's why we have the I in front of us. The cosine, however, will always give us the x value, the real part in our graph. It's very important to remember that the 5 in front is a scaling factor for both cosine. So we need to remember the C stands for cosine. So we have 5 cosine pi over 2. And then we have I, the imaginary number. And then we have S, sine. But we still need 5 sine pi over 2. Now, R is going to be our direction. So that is 5 in this case. We get R times cosine theta is going to be A, our real part, while R times sine theta is the imaginary part. And remember, here is no I because the imaginary part does not have the I in it. It's a real number that is multiplied by I. Now, first of all, we need to have a look at what our complex conjugate is. You should know very well what this concept is by now because you've used it countless of times. If we have a complex number a plus bi, then the complex conjugate is a minus bi. And I'm very sorry, I could not figure out late at night when I was doing this presentation how to put the bar on the top of the z. Some people actually write z star or z asterisk, for the complex conjugate. Now, in your exam, it will always be a z with a bar on top. And you can actually see this here in the picture where we have z bar. Yeah. So if we want to look at the complex conjugate, that just means we keep the real part the same, but we negate or we flip the sign for the complex part, the imaginary part. Sorry. So in the picture, we can see z is a plus bi over here, and z is a minus bi at the bottom. We kept a the same. A is, remember, the real part, which we can see on the axis. So what did that actually do? The real part is the same, but we changed the sign. Yeah, we know this. What about the symmetry? Yeah, complex conjugate is a function of symmetry. All we're doing here is we're taking our complex number, wherever it is, and we're using symmetry or reflection by the x-axis or the real axis to get to our complex conjugate. We can also see that here, our angle theta that we had for our previous z, for the complex conjugate, it makes the angle negative. So 3 plus 2i, what's the conjugate? Very easy. We just flip the sign for the part that has an I. So 3 minus 2i. Now in polar form, this is basically very similar, yeah, but we just need to remember what we need to do. So the modulus remains the same. The modulus is another word for the radius or for r that we have seen so far. It's the more precise term for this. The angle changes sign, yeah. Just remember, we in complex numbers for your exam, we encourage you, or we prefer for the marking schedule, that you write your complex numbers with an angle between minus pi and pi. So what does that mean? We have our 0 here, and if we go this way across, then this is going to be our angle 0, pi over 2 all the way to pi, because a full rotation is 2 pi, but we're only going halfway. That will be pi. This is the same as 180 degrees. Pi is 180 degrees when you convert it from radians to degree. But instead of going further than that axis and making it a reflex angle, we start again at 0 and we go the other way. We start at 0 and we go backwards. And because we're going backwards, now we're using negative pi. So whenever you write your angle, you should try and keep it within this value. Awesome. So let's have a look at the example for a polar form. If we have 3 cis 0.5, remember the 3 represents how far we are away from the middle. That doesn't change. The only thing that changes is our angle. And if our angle was positive, our angle is the same value, but negative. So 3 cis minus 0.5. Okay, now we know what complex numbers are. We know how we structure them. We've got 2 ways, rectangular form and polar form, on how to write them down. So let's do some calculations. Shall we start with adding and subtracting? Let's have a look at rectangular form. This is actually very, very easy to add these complex numbers together, and it is basically what you've been learning since primary school, just now with an imaginary part. So adding the real parts together and adding the imaginary parts separately, that's basically all we do. The formula here, you can see a plus bi plus x plus yi. I used both the notations that people usually use and added them together. And here we can see a is the real part of the first one, x is the real part of the second one, which means the real part in the answer is a plus x. Whereas b and y are the imaginary parts. So if we add them together, we add the imaginary parts together and then multiply by I. Subtraction is just as easy. It's exactly the same rule. We're going to do the real part minus the real part, the imaginary part minus the real part. Very easy. Please note that converting to rectangular form before you have a complex number that you want to use here. We don't want to add or subtract in complex numbers in polar form. Now, in terms of multiplication, let's again start with rectangular form. Yeah, for adding and subtracting, we didn't do polar form because we're not going to do that ever. we're always going to convert our number to rectangular form first, then add or subtract if we have to. So let's have a look at multiplication. Let's start with rectangular form. So we need to know the rule. Well, this is what you've been practicing for in the last couple of years, expanding brackets, that's all it is. If we have 5 plus I multiplied by 3 minus I, two different complex numbers, they don't have to be different, yeah, but if we're multiplying two complex numbers together, we can write them in rectangular form and just expand the brackets. And here we get 15 minus 5i plus 3i and minus I squared. And we're going to use the definition that we had right in the beginning for our complex numbers, where we said that I squared is equal to negative 1. So we're going to get negative times or negative of negative 1, which is going to be a positive 1. So we have a positive 1 here and a 15, making it 16. What about polar form? Well, polar form is actually quite easy to multiply, yeah? Unless adding and subtracting, which we never do in this form, we want to actually multiply and divide in this form. Let's have a look at the rule. Multiplying the moduli. That is what we do. We just multiply the R value and then we add the angles together. Well, let's have a look at an example. It is as easy as that. If we have 5 cis pi over 2 times 2 cis pi over 3, then all we do is we multiply the modulus together, so that's 5 and 2 to become 10. We copy the cis because it's still a complex number in polar form, and what do we do with the angles? We add the angles together. So, in a sense, when we multiply complex numbers together, what it does, it makes the distance different. It scales the distance that we are away from the origin. Yeah, here the complex number is now further away, 10 units away from where we start off in the origin. But what do we do with a pi? So when we multiply complex numbers together, we add the angle. That means we're shifting where we point to in the argand diagram. So multiplying complex numbers is a combination of scaling how far we're away from the origin and rotating counterclockwise through the origin. Now, for multiplying, just remember our rule: modulus multiplied together and the angles added together. Well, division in rectangular form, well, let's have a look. We can have two complex numbers and we're just going to divide them and see what happens. And we're going to follow the same idea that we previously had with our surds. We don't want to have a complex number where we have a fraction and in the denominator we have another complex number. So we again use the knowledge that we've had before for our expanding with multiplying by a fancy 1. So let's have a look. If we have 1 plus I divided by 1 minus I, what we want to do here is we want to multiply by the complex conjugate, the conjugate of the bottom, which I see now I did not do here. Must be a typo. Sorry about that. It should be 1 plus I divided by 1 minus I is multiplied by the complex conjugate, which is 1 plus I and 1 plus I. So both of these terms should be 1 plus I. Now, if we are having a look at division in polar form, it is just as easy as multiplication in polar form. Multiplication and division is what we want polar form for. So, just like before, we multiplied the moduli. Well, now we're going to divide them. Easy as that. If we're dividing a complex number, well, we should divide the moduli. Makes sense. And before, when we multiplied, we added the angle, so we shifted our complex number through as we multiply. Well, if we divide, we need to undo that, so we're going to have to subtract the angles to make it opposites of each other. Let's have a look at a couple of examples, and talking about is always more difficult than just seeing it and see what happens. So 10 cis pi, which we had before, divided by 2 cis pi over 2. Well, 10 divided by 2 becomes 5. The moduli are just divided, just like normal numbers. You can put it in the calculator and it's done. We copy the cis because it's still a complex number in polar form. And then we do pi where we start, minus pi over 2, which is pi over 2 again. So rectangular and polar, why do we want to? I kind of already said that. We want polar form for multiplication. But it didn't seem too difficult to do multiplication with rectangular form. So let's have a look. We want addition and subtraction in rectangular form. This is a must. Yeah. Now, we can still do the expanding part that we've seen before when we multiply to complex number in rectangular form. The problem becomes when we do a lot of multiplication questions. Let's say, for example, 1 plus I, all to the power of 100. Are you really going to be happy expanding brackets 100 times and simplifying each time? That's going to take you a long time. In polar form, it is just one calculation, boom, done. Now, one topic that is very important for complex numbers, we do this all the time. We compare when two numbers are the same. In the real numbers, it's very easy. When is the number equal to a half? Well, if it is equal to half, nothing else. The fractions actually give us a good example here. 1/2 and 2/4 are actually the same. Yeah, so even in our real numbers, we have different numbers that are the same. So now for our complex numbers, if you want to know if z and x, or whatever you want to call your complex numbers, are the same, we just need to check two things. Are the real parts the same and are the imaginary parts the same? Think about how we draw these complex numbers on the Argand diagram. If we just have our coordinates and we're going to the same position, then there must be the same number. Just a reminder, this is often used in exam conditions, under exam conditions. All the time they're going to ask you, when is z divided by 1 plus I equal to 3 plus I? Yeah, they're always going to put this. Or they're going to give you a question where there's a k, a scale factor in there. Z is equal to 2 plus ki. When is z squared equal to something else? So let's have a look at a question here. Z, just like I've just mentioned, z divided by 1 plus I is equal to 3 minus 2i. So which complex number z can we substitute in here to make this equation true? The way that we start these questions, and in year 13, you're really starting to think about proofs, to think about how equations work. We can write the whole thing on our test paper and continue step by step through, but it's much easier if we start at one side and we end with the other. So here we start with LHS. I usually write that for left-hand side, and RHS, which stands for right-hand side. So the left-hand side is this, the right-hand side of this, depending on where the equal sign is. So we're going to simplify the left-hand side and write it in the form a plus bi. And we're going to see what happens. So first of all, how do we do this again? Well, remember, if we're doing anything with z, we need to write z is equal to a plus bi. We cannot solve anything if we have a complex number that doesn't have the form a plus bi, real part plus imaginary part. So let's substitute that in. So we're going to get that z is a plus bi, and we're just dividing by 1 plus I like we normally would. But again, how do we do this? It's division, dividing by 1 plus I. How do we divide by a complex number in rectangular form? Well, we multiply by the conjugate in the numerator and the denominator. Let's see if I did it right for this one at least. Yes, so I actually can do this, I promise. So a plus bi divided by 1 plus I, and now we're multiplying by a fancy one, which is the conjugate of the denominator. Cool. And now this is just a little bit of algebra. Remember to put brackets at the top. A plus bi is in brackets and 1 minus I is in brackets. And the same goes for the bottom. Then we can expand these questions and get the correct answer. I believe that you can do the expanding here, so I'm just going to go through. You have the notes right here. Try it yourself if you don't trust yourself and see if you get the same answer as me. Now we have expanded over here. What do we want to do next? Well, here we're always going to rearrange so we get a real part and an imaginary part. So here I see A, and if you think about I squared being -1, which makes this a positive, this is just B. Positive B and positive A. These don't have an I. So these are our real parts. Here we have BI and minus AI. Both have an I, so they're both imaginary parts. So you can think of this as factoring out the I. We're just going to add the coefficients. Minus A added to B. Well, and if you do minus A plus B or B minus A, it doesn't quite matter. Now, at the bottom, your I should always fall away. This is why we're doing that. We're getting rid of I's in the denominator. And remember, we're always got a minus. We've got 1 squared, we've got I squared, and always have a minus in front. So we're adding these together, and I squared is -1. So 1 plus 1, which gives us 2. When we're here, now we always want to write our complex numbers in rectangular form. A plus BI. Now, A and B might be different here, but a real part plus an imaginary part. So what we can do here is we can split our fraction into just the A plus I and the B minus A. So let's have a look. We have A plus B divided by 2, and then we have B minus A divided by 2. And we just split the I behind it because we just keep track of where the imaginary part is. Now what we did is we wrote our complex number that we had at the top, z over 1 plus I, in the form that we want. This is a simplified form. It's longer, yes, but we have it in the form that we want in terms of a real part and an imaginary part. And remember, what do we need to compare two complex numbers? We want both of them to be in rectangular form where we can compare the real parts and the imaginary parts. So let's do that. Let's get our question back. 3 minus 2i is what we want to compare it to. So we already calculated the first part, which we can see here on the screen, and it should be equal to 3 minus 2i. So we're going to match the real part and the imaginary parts. Our real part here is a plus b over 2, so we're going to match it with the real part for the other number. And our imaginary part is b minus a over 2, remember no I, equals to the imaginary part here. We now have two equations and two unknowns, so we can solve for a and b here, which are simultaneous equations. Yeah. If you do this correctly, I assume you can just need to multiply this by 2 to get a plus b is 6. Here we multiply by 2. B minus a is minus 4. You can use your calculator to do simultaneous equations, or you can use elimination method, or you can do substitution method. Write one equation as a equals. Yeah. For example, this one here is a equals 6 minus b, and we can substitute that in there and solve for b. Everything you do here is going to work. Awesome. Now, comparing complex number in polar form, well, it's basically the same thing. In rectangular form, we want the real part and the imaginary part to be the same. it makes sense that in polar form, we want the modulus, the distance, to be the same as the angle. Just saying, this doesn't normally happen to come along in exam questions, but you can convert your numbers to polar form and compare them then. That works. It's up to you. Again, we want the same angle and the same modulus. Yeah, but I just want to say one thing. If we talk about the angle, remember that if we go full circle and keep going, we can keep going around, each time being 2 pi or 360 degrees. That means if we have our complex number, let's say we have I, which is on the coordinate system, it's just at the top, it just goes up. Sorry, we have a 90-degree angle. We could also have 90 degrees plus 360 degrees. So it might not always look the same way when you compare complex numbers in polar form. Just be careful of that. But if you stick to the rule that your angle is always between minus pi and pi, then you're going to be fine and you can use this without having to think about it. Okay, so 1 second. So we have de Moivre's theorem. Yeah, again, a theorem, one of the rules that we really want to know. So, de Moivre's theorem is talking about integer powers of complex numbers. And this refers back to what I was talking about earlier on, where we had 1 plus I to the power of 100. Yeah, we want powers, but we want integer values. So we want to have numbers that are 1, 2, 3, maybe a negative. So let's have a look. When do we actually use this? We want to use this when we're calculating higher powers of complex numbers. And we want to use it when calculating any root of complex numbers. The value, it says integer powers, it's a little bit loose. We can also use this for fractional powers. So let's have a look. Usually, yeah, that's right. The second one is where we want to really use this. You don't usually need to remember the name, but you need to remember what it does and when to use it. That is important. So the rule is quite easy. It follows just straight from what we know from multiplying a complex number together. In polar form, yeah, we want to do this in polar form only. Yeah, so we want to write our complex number as a distance r, the modulus, times theta to the power of n. So we want to have some power for our complex number. So, and the way that calculating multiplication works for polar form is, remember, we multiply the modulus. 2 cis something times 5 cis is 2 times 5 is 10, 10 cis. Yeah, but if our complex number has modulus r, then it's r multiplied by r multiplied by r and so on n times, because we're multiplying it to the power of, well, to the power of n, which means multiplying it by itself n times. So we're just going to end up with our modulus r to the power of n. And it's just, like I said, if you do the calculation, it's just a 1 step, well, 2 steps, because you have to do it for the angle, calculation, and you're done. No expanding brackets 100 times, no back and forth, no simplifying, well, to a small degree. But now we also have to remember, if we multiply the complex number multiple times, each time we multiply, what did we do with the angle? We added the angle each time we multiplied by a complex number. So we're going to have to add the angle each time. If our angle here is theta, and we're multiplying this complex number n times with itself, then we're going to add theta n times. We're going to have plus theta, plus theta, plus theta, plus theta, n amount of times, which is going to be n times theta. As long as you remember this formula, that if you have a power, the modulus keeps the power, so r to the power of n, but the angle is just multiplied by the power. then you're good to go. Try to do remember how it works though. Let's just see a very quick example. It's very easy. If we have a complex number, 2 cis theta, and you can have for theta, you can have anything, pi, 0.5, it doesn't matter. Yeah. So the number in front, the R value here is 2. The modulus is 2. So we get 2 to the power of 5. We keep the cis, it's still in polar form. And then 5 times the angle, 5 times theta. That was a very quick and easy calculation. Yeah. Now it becomes more complicated, but this is the one that they use in basically every exam. They use exactly this calculation, and as long as you remember the steps that you need to take, which was just 2 steps, easy, you can solve the harder questions in the exam. So let's have a look. Z to the power of 4 is equal to 1. This is a very common question that they have in some form in the exam. Whether it's a power of 3 or 4, I'm not sure. It might be any of those. So what does that mean? Well, which number multiplied by itself 4 times gives you 1? Well, clearly 1 and minus 1, right? We already knew that. 1 times 1 times 1 times 1. Cool. -1 times -1 is positive. -1 positive. 1 times 1. I mean, that was an easy one. But remember what we said before. A quadratic equation with squared always has 2 solutions. Here we have z to the power of 4. That means we need 4 solutions. We only have 2. So how do we actually find all of the solutions? I'll give you a step-by-step guide, like an algorithm, on how to solve a question similar to this. Basically, you just need to follow the steps, but please try and remember what we're doing and which concepts from before we're using for one of these questions. Okay, so let's have a look. We always want to write it in polar form. Why? Because it's multiplying by itself 4 times. We don't want to be expanding. So that's easy. If we now have a look here, if we have z4 in polar form, then we also should have 1 in polar form. So let's write 1 in polar form as well. So 1, think about how 1 works, where it would be in the arcade diagram. You have the real part is 1, and then the imaginary part is 0. So we're going to be going 1 distance along the x-axis, along the real axis, and our angle is 0 because we're going along the real axis. You need to know how to transform a number like this, a real number, into polar form, which is exactly this step. Basically, it's the same number that we want to transform with the angle 0, as long as it's real. So now what do we need to do? Remember how I said that in polar form, the angle matters. We can actually go all the way around the circle and we're back at 1. And we can go all around the circle again and we're back at 1. So here, for this calculation, it is critical. This is the step that will give us the answers. Is we have to consider 0 for the angle, but plus 2n pi. Why n? N is just any number. It is actually an integer. It can be a positive or negative whole number. So this means we're adding 2n pi, remember that's 360 degrees, as many times as we want. We're going to keep going back to 1. So this is the same thing. We're going to write 1 CIS of 0, but we're going to add 2n pi, and it's always plus 2n pi. You always do this step, write it in polar form, add 2n pi. Bonus point, if I was marking it, if you tell me that n is an integer, usually in the marking schedule they ignore that. Now we can apply the theorem. Yeah, so we have written our number, yeah, and 0 plus 2n pi, remember it's just 2n pi. So if we want to get to z from z4 to z to the power of 1, we need to take the 4th root, so to the power of 1 over 4. To make it look better, I just wrote to the power of 0.25. And how does that work? Remember, we take the modulus 1 and just raise it to that power. Whatever we're doing, we're raising that one to the power. 1 to the 0.25. Well, you can use a calculator, or you should know that is 1. But also in the brackets, what did we do? We multiply the power by our angle. So 0.25 times 2n pi. Now we can actually find all the 4 solutions. And what we do is we pick numbers for our n. We go around the circle a few times. So let's start with n is 0. You should always start with 0. Now, it doesn't actually matter because the solutions you're going to get are going to repeat. But just remember, start with 0 and end with one number before what you should have. Z to the 4 should have 4 roots, so you end with n3. But we're just going to start with n0, and we're going to keep going until we have 4 answers. So the first one is if n is 0. So we substitute that in, then we get 1 CIS. Well, and if we substitute in 0, that's 0.5 times 2 times 0, which is going to be 0. Put that in, we know that's going to be 1. Now, we have one of our solutions over here now. If we're putting in the next number, we're going to put in n is equal to 2. We get what we have here in the top. We're going to get 1, which comes from this, CIS, and then we're going to have here 2 times 1 times pi, which is 2 pi, but a quarter of 2 pi is half pi, so we're going to end up with this. For our third solution, we substitute in n is 2, so we're going to get 2 times pi, which is 4 pi, but a quarter of 4 pi is pi. And then the same way you get this fourth solution. And here we can, if you have a look at this, if you want to transform this to rectangular form, which we have here at the end, then remember we need to do what we discussed before. What does cis mean? Cosine of the angle plus I times sine pi over 2. So the real part is cosine, the imaginary part is sine. Cosine of pi over 2 is 0, sine of pi over 2 is 1, which is 1i. Now, taking the nth root of the complex number is exactly what we did here. So here we had z to the power 4 is equal to 1. Let's see what actually happened here. I have drawn the diagram with all 4 solutions, 1, -1, I, and -I, just like we have just found out. What can you see? Well, it looks like all of the solutions lie on the same circle. They're all the same distance away. We also note that they are the same distance from each other, and there's 4. Let's have a look at z to the 5 is equal to 1. The same thing happens. We're going to end up with 5 roots. They're all going to be on the same circle, and the circle is going to have radius of r to the power of 1 over 5, because we're taking the 5th root. And again, we see that they all go around the circle with the same distance away from each other. Well, nothing crazy here. Z to the power of 20 is 1 will give us 20 solutions that are all equally distance spread around the circle. So remember, and we've spoken about this already, if you want to convert from polar form to rectangular form, which you might want to know, is quite easy. But remember the meaning of CIS. Cosine of the angle is the real part, sine of the angle is the imaginary part. You just put that in the calculator and find your values, and you're good to go. Quick example, what is 2 CIS of 0.3? So it's 2 times cosine of the angle, 2 cosine 0.3. And the imaginary part, remember the 2 in front, that's what students usually forget, is 2 times the sine of the angle. We can use our calculator to figure out what that is, but make sure that your calculator is in radians. If we want to go the other way around, from rectangular form to polar form, you might want to do that for a question where you have lots of multiplication or dividing to do. So how do we find the modulus? Remember, the modulus is how far we're away from 0. It's the distance I'm giving you from the origin. So if we have a look at our complex number here, we have our complex number 3 plus 4i. And we want to represent this now with a modulus, a distance away from the origin, and an angle from the x-axis, the real part. So in general, we can use the formula that z with bars, so the absolute value of z, or you should call it the modulus of z, is equal to r, the radius, which is the square root of the real part squared plus the imaginary part squared. This should be in your formula sheet, but you should know this one by heart because this is one of the most fundamental concepts in complex numbers. We can also use trigonometry to find the angle because we can have a right angle triangle using our coordinate form just like before. And if we want to find the angle here, we always have the opposite divided by the adjacent, which is tan. And to find the angle, we do the inverse of tan, tan to the negative 1. Again, there's a formula in your formula sheet, arg z. You need to remember what this means. This is the argument of the complex number z, which means the angle theta, is given by the inverse tan, or the arctan, whatever you want to call it, of the imaginary part divided by the real part. And remember, the imaginary part does not have an I. I will say that 100 times, and people will, under exam conditions, forget, and this will not work for them. So, even though you have a formula here, there is a little trick or a little complication when it comes to our complex number. It will give us an answer regardless of what we put in, because the calculator will give us one. However, it might not be the angle that we actually want to look at. Yeah. So let's have a look why we need to be careful. I recommend drawing a diagram every time you transfer from rectangular to polar form. And it doesn't have to be accurate. The only part that we're interested in here is in which of those 4 quadrants our complex number is in. Now, you can see the quadrant 1 has positive real, positive imaginary, and you can kind of think of which one you're in just by using your knowledge about coordinates. Now, again, we have our general formula, but if we want to use it, we need to draw a quick diagram to make sure we get it right. And this is the reason why. If we are now using the imaginary part divided by the real part, yeah, this is the opposite over the adjacent, then we're finding the opposite is the imaginary part over the adjacent is the real part. So we're finding this angle. But this is not the actual angle that we're looking for. We want the angle from the x-axis starting at the positive part all the way to our complex number. So from here to here. We don't want the angle that the formula is actually finding. This formula here will give you the answer for finding the angle if we are in this quadrant at all times. Yeah. So your formula, tan inverse of imaginary over real, will work for quadrant 1 and quadrant 2. It will fail for quadrant 3 and quadrant 4. But all we need to remember is that the difference is 180 degrees. We just want to move this angle to the other part over here. Basically, angles on a straight line is 180, so 180 minus this angle. But 180 is for degrees. All of our calculations for polar form are in rectangular form, are in radians. So instead of 180 minus, we got pi minus. Yeah. Okay, so this is for this quadrant here. The next part here, if we are in the bottom quadrant, we have the same problem. If we're looking at our inverse tan of imaginary over real, we're going to have the imaginary part is the opposite, the adjacent, the real part, and we're going to find the red angle. But we don't want the red angle. We want the angle that starts in the x-axis, the real axis, and goes all the way across counterclockwise if it's underneath. So again, we do the same thing. We do kind of 180 minus this angle, so pi minus the angle. But the problem with that is the answer is not going to be within the range that they want for the exam, which is that the angle is between negative pi and pi. So for quadrant, I think it's quadrant number 4, the one where both are negative, we need to have this formula, minus pi minus the arctan. So we have both of those equations, this one here for the quadrant in the corner in the top, and then the same with a negative for the quadrant at the bottom. Apparently this is 3. It was 1, 1, 2, 3, 4. Now, these formulas here are not going to be in the formula sheet. You either need to draw a picture to remind yourself you have to add pi or subtract pi, or you can simply remember those two formulas that I've given to you by heart, which just needs to remember which one has a negative in front of the pi, depending on which quadrant you're in. Then you can use the formula and you don't even have to worry or think where you need to go. Okay, thanks for staying all the way through for all these topics. And as promised, there will be a surprise at the end. So it is now time to test yourself. Yeah, we've gone through all the concepts in the complex number examination. Everything that you need to know. If there's other parts that you're struggling with in the exam, it is all algebra related questions. All the concepts that we have discussed today can be applied for all of the questions in the exam. The reason why those might seem a little bit harder is because it will require you to do algebra to find certain values, to find a k, yeah, but the actual fundamental concepts are all covered in this course. So there's going to be a worksheet that's available with questions from each of the concepts that we discussed today. I'll leave that in the link below so you can test yourself to make sure all of your questions, all of your fundamentals, all of the knowledge that you require as a whole is ready for the exam. Now the difficulty level for this worksheet is going to be rather low, maybe a little bit medium depending on some of the questions. But I really want you to focus to make sure all the conceptual knowledge, all the steps that you need to take are fully understood and that you can do them fast and easy without having to think too much. Because when you do complicated questions, the fundamental knowledge should already be there, helping you, showing you what to do. The rest is going to be algebra, simplifying, and whatever you've learned in previous years in algebra. Now, as we said, the goal is to master the fundamentals. Yeah, and in the next stream or the next video that I'll upload for complex numbers, it will also be in the 2-hour format, but we will go through worked examples for the whole duration of the 2 hours. Make sure that you're confident with all the fundamentals that we talked about that will really push you in our next video. Awesome. So now what? Make sure you know all the fundamentals that we've talked about. Use the worksheet to practice the examples. Pause the video, go back to your notes where you wrote down what you were needed, what you had to remember. Do your cue cards as we discussed in the beginning if needed. And if you're stuck with any of the fundamentals or need any last minute help, you can always ask for help. I will leave the link for the tutoring for one-on-one sessions in the description as well. Wonderful. Thank you very much, and I'll see you in the next video.